Good afternoon. I'm Good News Agbonzi Kilo, and this is my ECE600 final presentation on a self-propelling microfluidic device based on particle-localized electrokinetics. I'll cover the device concept, the three driving mechanisms, key performance data, our testing approach, and how it compares to existing technologies. The core idea is simple but powerful. Instead of bulky external pumps, we use microparticles themselves as the active components inside a small chip. Apply a low voltage AC or DC field, and these particles trap, sort, propel, pump, mix, and even help detect cells and biomolecules. The image on the left shows the actual chip held in a researcher's hand, demonstrating how compact and portable this technology really is. On the right are the six core capabilities the chip supports, all on a single integrated platform. Three electrokinetic mechanisms power the device. First, diode rectification. A diode in the channel converts AC into a local DC component, generating steady flow at low voltage. Second, induced charge electrophoresis on Janus particles. These half metal, half dielectric particles develop an asymmetric charge cloud and self propel under an AC field. Third, dielectrophoresis, which uses non uniform fields to assemble particles into ordered structures. Together, these give us a complete toolkit for moving fluids and particles with no moving parts. Now, the key performance data. The diode pump operates at fields as low as 93 volts per centimeter, well below the threshold for damaging biological samples. It's stable across pH 4 to 6.4, covering most diagnostic conditions. The Janus ICP shows a clear frequency response from 20 Hz to 12 kHz, with peak propulsion in the kilohertz range. Response times drop from under 5 seconds at startup to a steady 15-second cycle. The two charts on the right confirm the diode velocity curve and the ICP frequency band, both consistent with VELEV 2009. For testing and validation, we follow a four-step workflow. First, fabricate the chip and verify electrode geometry under SAM, as shown on the right. Second, characterize the response by sweeping voltage and frequency while measuring particle velocity with high-speed video. Third, validate flow stability and reproducibility across multiple chips. Fourth, qualify the device against 6 acceptance targets, covering field strength, pH tolerance, frequency range, response time, particle uniformity, and channel integrity. A chip is only released once all 6 are met. This framework is adapted from my midterm report. How does this compare to existing microfluidic technologies? Advantages: no external pumps, low voltage, integrates trapping, propulsion, and detection on one chip, scales to multiple channels, and uses standard photolithography. Limitations: sensitivity to electrolyte conductivity, moderate Janus particle yield, electrode fouling under sustained DC, biocompatibility for live cell work still needs validation, and limited long-term reliability data. So while promising for diagnostics and research, those limitations are exactly where the next round of engineering will focus. This analysis comes from my research disclosure assignment. To wrap up, why does this matter? Particle localized electrokinetics gives us a self contained, low power, scalable platform that combines fluid handling, particle manipulation, and sensing on one chip. Three pillars of impact. For research, a flexible testbed for colloidal dynamics and active matter. For device design, a path to portable, pump free lab on chip systems. And for diagnostics, low cost, point of care assays. Next steps: improve Janus yield, characterize long-term electrode stability, and demonstrate a full diagnostic assay end-to-end on chip. Finally, the references. The primary source is Velev and colleagues, 2009, in Soft Matter, the foundational paper on particle-localized AC and DC manipulation. Additional sources include Gangwal 2008, Hermansen 2001, Squires and Bazant 2006, Chang 2007, and my own ECE 600 midterm report. Thank you for your attention. I'm happy to take any questions.